Hello everyone. Today we are going to look at two binary operations. One is distributive over the other. I'm going to discuss how to construct the operations of good properties using isomorphic algebraic structures. We define two operations. The first one we call circled plus. A circled plus b is defined to be a plus b minus 2. Another one, a circled times b, is defined to be ab minus 2a minus 2b plus 6. For example, 3 circled plus 5, so 3 is a, 5 is b, would be 3 plus 5 minus 2, which is 6. 3 circled times b would be 3 times 5 minus 2 times 3 minus 2 times 5 plus 6, which is 5. We can check. Both of the operations are commutative and associative. That's not difficult to verify, but here we verify a distributive property. The circled multiplication is distributive over circled plus. First of all, the left-hand side, a circled times b circled plus c equals a circled times, we first expand b circled plus c. By definition, the b plus c minus 2. And then, using the definition of circled times, would be the first parameter a times the second part b plus c minus 2 times a minus 2 times the second part plus c plus 6. Clean it up, we have ab plus ac minus 4a minus 2b minus 2c plus 10. Now we look at the right-hand side. A circled times b circled plus a circled times c. The first phrase is a circled times b. By definition, ab minus 2a minus 2b plus 6. And the second part, ac minus 2a minus 2c plus 6. Then, using the definition of circled plus, would be the first operand plus the second operand minus 2. Combine the like terms, we got the same result. So, we established the distributive property. Here is the question. How to construct operations that one is distributive over the other? So actually, you can arbitrarily construct binary operations pretty easily. However, most likely the one won't be distributive over the other. In fact, I constructed these two operations by a special techniques. So the answer would be using isomorphism of algebraic structure. So what are algebraic structures? An algebraic structure consists of a non-empty set A, also called the underlying set, carrier set, or domain, equipped with a collection of operations on A. Typically, these operations are binary. We have two examples. The first one, all real numbers with two binary operations, plus and multiplication. The second example, all real numbers equipped with circled plus and circled multiply. We can see these two algebraic structures are similar in many ways. One of the tools investigating such similarities is called isomorphism. An isomorphism is a one-to-one and onto mapping from one algebraic structure to another that preserves the operations. So what do we mean by preserve the operations? I give you an example. I claim the function f of x equals x plus 2 is an isomorphism from the first algebraic structure to the second. Let's look at the plus and the circled plus. In the first structure, we have 3 plus 4 equals 7. And we know f of 3 is 5, f of 4 is 6, and f of 7 is 9, the plus 2 function. Then 5, 6, and 9 are in the second domain, and also 5 circled plus 6 equals 9. Or f of 3 circled plus f of 4 equals f of 3 plus 4. We have a similar story for multiplication and circled multiplication. We have 3 times 4 equals 12. And f of 3 again is 5, f of 4 is 6, and f of 12 is 14. Then in the second algebraic structure, we have 5 circled times 6 equals 14. You can verify that. Or f of 3 circled times f of 4 equals f of 3 times 4. In general, we can verify that f of a plus b equals f of a circled plus f of b. F of a times b equals f of a circled times f of b. Those are what we mean by preserving operations. We can prove the distributive property of the second algebraic structure using the isomorphism. Let f of x equals a, f of y equals b, and f of z equals c. Because f is one-to-one and onto mapping, then we can have the inverse of arbitrary real numbers a, b, and c. So from the left-hand side, we can replace a, b, c with f of x, f of y, and f of z. Then, because f is an isomorphism, it carries the operation from plus to circled plus, then f of y circled plus f of z equals f of y plus z. Again, f is an isomorphism from multiplication to circled multiplication. We have the equality equals f of x times y plus z. So now you see all the operation in the second structure is mapped to something in the first structure. We know multiplication is distributive over addition. We have this expression. And then we go back to the second structure again using the property of isomorphism. From plus to circled plus, from multiplication to circled multiplication, and then replace f of x, f of y, and f of z with a, b, and c respectively. We are done. So you see, in this proof, we didn't use any details of the definitions of circled plus or circled multiply, like a plus b minus 2 or whatever. We only rely on the isomorphism and the property, the distributive property in the first algebraic structure. In other words, as long as the two algebraic structures are isomorphic and the operations in the first structure is distributive, then the distributive property is automatically carried to the second one. Isomorphism also preserves special numbers. In the real number with plus and multiplication, we have two special numbers, 0 and 1. Any number a plus 0 equals a times 0 always 0. And for 1, a times 1 equals a. And f map these two special numbers to 2 and 3 respectively. Then, in the second algebraic structures, 2 and 3 should be the special numbers. We can take a look. A circled plus 2 equals a, that's a plus 2 minus 2 equals a. A circled times 2, by definition, a times 2 minus 2a minus 2 times 2 plus 6 equals 2. Always 2, independent of the value of a. And for the other number 3, a circled times 3 is 3, a times 3 minus 2a minus, there's typo, a times 3 plus 6, which is a. Now, we go to the last topic, how to construct new operations using isomorphisms. This time, I assume f of x equals x plus 2 is an isomorphism from the regular plus and the multiplication to circled plus and the multiplication. I pretend I don't know the definition of circled plus and circled multiplication. Then what should be circled plus and circled multiplication? How do we define them? This is a numerous question. Here we go. We know a circled plus b. By definition, a is f of a minus 2 circled plus f of b minus 2. And then we know f is an isomorphism. It preserves operation from plus to circled plus. Then we have this equality. So cleaning up, that's f of a plus b minus 4. And then we know the definition f is a plus 2 function. So we end up with a plus b minus 2. That's how I defined this binary operation to begin with. Similarly, for circled multiplication, we have a circled times b equals f of a minus 2 circled times f of b minus 2. And It preserves operations from regular multiplication to circled multiplication, and we expand it f of ab minus 2a minus 2b plus 4. Then f is plus 2 function. We got this. Finally, I have an exercise. Try another isomorphism, gx equals cubic root of x. And you can see, you can try. So how should you define your circled plus and the circled multiplication? That's all I have today. Thank you for watching.